Welcome to my Cisco Scaling Network lecture review. Here we're doing Chapter 7. This is our first section on EIGRP, also known as Enhanced Interior Gateway Protocol. We finished with OSPF, and now we're moving on to the next major routing protocol. We're going to do an introduction, characteristics, configure, operate, and then configure EIGRP for IPv6. Again, this chapter is just more of a basic overview, nothing too, super in-depth. We're going to talk about some of the features and operations of EIGRP, the packet frame. We're going to be looking at calculating the composite metric using the dual or the diffusing update algorithm. We're going to again look at the concept and operations of dual for like a slide or two, and examine the commands to configure EIGRP both IPv4 and IPv6. So let's look at some of the characteristics. It was released in '92 as a Cisco proprietary protocol. Its basic functionality was released as an open standard in 2013. So it's not 100% open, but I mean it's getting more open. It uses an advanced distance vector routing protocol. Part of that protocol uses the diffusing update algorithm to calculate path and backup paths. It does establish neighbor adjacencies. It does use the reliable transport protocol to provide delivery of EIGRP packet neighbors. It does have partial and bounded updates. Send updates only when there is a change, and only to the routers that need the information, so not every one. It does support equal and unequal cost load balancing. So on that slide, the two big things that I thought was very interesting is the advanced distance vector routing protocol. Remember, two major types of routing protocols, distance vector and link state. All of that was discussed in the first installment of the Cisco material, which is the fundamentals of networking. And again, it's becoming more of an open standard. So that was kind of important. So let's go ahead and look at the protocol dependencies. Here we have two neighbor, two topology, two routing tables, and you'll see that they're dealing with the next router, the next routing table, but it's always looking at the IPv6 table, then the IPv4 table. So that's getting more interesting. If we talk about the reliability transport protocol, again, looking at the PDM. So what is the PDM again? I'm going to go back one slide. Protocol dependent modules, meaning each of these are completely independent of one another. They may work together, but they're two separate items, or two separate entities. PDM, protocol dependent modules. Here we have an application layer for IPv4 and IPv6. We have the reliable transport protocol. It is being EIG replaces TCP with the RTP. So this guy right here, while it's not TCP, it's probably slowly going to be replacing TCP in some aspect. I get lots of articles that say both that it will and that it won't, so just I'm thinking it has a strong possibility later on, but we'll see. So this guy right here is the TCP/IP structure. If we're looking at the OSI model, we have a few more layers that are missing, but TCP hierarchy, application, transport, layer 3, also, or TCP layer 2 is internet. That's going to be our routing protocols, and then network access is the last two. So if we're looking at OSI, 1, 2, 3, 4, 5, 6, 7 for OSI, because this one is using the TCP IP hierarchy. So again, remember the PDMs, separate tables for each of them. So I mean, there are some differences between the different hierarchy models, so just keep that in mind. Authentication, very similar to OSPF. You can be configuring to authenticate so that routing information is exchanged and encrypted, basically ensuring routers only accept updates from routers with the appropriate authentication information. What gets interesting is EIGRP has different packet types: hello, ACK, update, query, reply. A hello is again a discovery. Acknowledgement is receipt of an EIGRP packet. Update will convey additional information. A query will be a request, and a respond will be to a query. So these two kind of go together. And update and acknowledgement and hello and acknowledgement kind of go together. Because again, acknowledgements is a receipt of a packet. So let's go ahead and look at the hello packet. It's basically used for discovering of the neighbor protocols. It uses a distinct multicast address. That's going to be a multicast address for EIGRP. Here it is for your appropriate IPv6 address. It's sent every 5 seconds. Every 60 seconds on lower speed NBMA type networks. Remember that an NBMA is a non-broadcast multi-access network. EIG uses a default hold timer of 3 times the hello interval before declaring neighbors unreachable. So if our hello timer is 5 seconds, the hold timer will be 15 because it's 3 times the hello time. So now let's go and look at the updates and acknowledgements. Again, you can send partial updates. You can send bounded updates. What I really like here is the partial updates only contain information about route changes, so you don't have to worry about send the entire routing table. It can just be, here's a portion of it. Because again, update packets are sent to propagate the routing information only when necessary, only if necessary. You can send bounded updates sent only to the routers affected by change, thus not having to resend everything to everyone. And again, once you send the update, an acknowledgement will be sent that will actually acknowledge that you received the packets. Next, let's look at the query and reply packets. So it's used for searching for networks. Queries use reliable delivery, which can be a multicast or unicast. The replies are also reliable delivery. So a query and replies both reliable and typically multicast or unicast. Replies are going to probably be unicast only, even though it doesn't say it. Alright, let's go ahead and move on to encapsulation of our different messages. So again, if we're talking about packets, layer 3, frame, layer 2, MAC address is going to be, again, the appropriate source and destination. And then here we may have the appropriate multicast address. And then the header for a packet. Alright. Because again, we're talking the type, the length, the values. Here you're going to notice things like the multicast, a protocol field 88 for EIGRP. The MAC address is going to be a multicast MAC address. That's not super important right now because that's not going to always be the MAC address. The packet header will be the opcode for EIGRP packet type and autonomous system numbers. And then the TLV type, again, EIG parameters, internal, external. I have not really needed to know this at the CCNA level. When we start doing our review for CCNP, you'll start getting more in depth with this. But for the CCNA level, this is more than sufficient. Here is the packet header and the TLV for EIGRP packet header a little bit further down. Again, version, the opcode, the checksum, the autonomous system number, the TLVs. So remember, the opcode for EIGRP packet types, update is 1, query 3, reply 4, hello 5. So if the opcode is 4, you know it's a reply. If you know the opcode is 5, you know it's hello. Here's again the opcode, query, update, I said those backwards, reply, hello. Those numbers will be important. I don't think you're going to be tested on them, but I mean just as you're analyzing the packet header, understanding EIGRP at that level may be useful. Alright, so let's go ahead and hop into the configuration of it. Configuring IPv4 for EIGRP. Again, here we're looking at bandwidth. If you can configure OSPF, you can configure EIGRP. EIGRP is honestly about the same level of difficulty as OSPF if you found that difficult. Here we're going to use autonomous system numbers instead of process IDs. So how to do this is you do router EIGRP and the appropriate autonomous system number instead of process ID, and that enables EIGRP processing. Again, like OSPF, the autonomous system numbers have to be solid throughout. Basically, it's just a sphere of control. It's only significant to the EIGRP routing domain, basically links all of them together. EIGRP autonomous system number is not associated with the IANA globally assigned AS numbers, so I'm going to start calling autonomous system just AS, because all of the EIGRP AS numbers are internal. So ISPs require AS numbers from IANA, so they will not accept a AS from EIGRP, which that's okay because we're not going to be routing across an ISP. BGP, which is another routing protocol, border gateway protocol, which does use IANA's AS numbers and is configured, is classified a advanced distance vector routing protocol, 1. 2 is the preferred routing protocol for the internet. But BGP is way outside the scope of this class because that's a CCNP level technology, and when we get into our courses for CCNP, that's when we'll discuss BGP a lot more in depth. So let's go back to EIGRP, how we configure it. In our example, we're going to use autonomous system number 1. So router EIGRP 1 will give us our subcommand for our config-router, and that's where we can do our statements. So used in both EIGRP and routing protocols, we have the router ID. Even though the router ID is more significant in OSPF, it does also exist in EIGRP. Here's an example, except instead of just doing router IP or router ID and then the address, we have to do EIGRP first, then router ID, then the ID that we're going to be using. If we don't set it, the loopback address can be used as the ID. If the EIGRP router ID value is not configured, the highest loopback address is selected. Again, that's how we do a loopback if we need to set one. Just like OSPF, we have to do network statements. One thing that I don't like is EIGRP is going to use more summarized type network statements. So here we have network 172.16.0.0, and so that's going to encompass both of them. And it's going to encompass any other network that is going to use that type of ID. Because there it will probably be using a, doesn't say it, but more of a /16. So it's matching the first 2 octets. So there's a lot of possibility for the 3rd and 4th. I don't like that, but that's how it works. The network statement for the second one, again, it's matching the first three. So this is more of a /24. And again, it gives you lots more space than what it really needs to do. I don't really like that about EIGRP, but it works. So we have the network commands, or the logging commands for them. So if you do EIGRP log neighbor changes, the router will configure it. It's on by default, but again, if you have to manually configure it, that's how you do it. It will display changes in the adjacencies to the neighbors. It will verify neighbor adjacencies during configuration, and it indicates when the adjacencies have been removed. We can do wildcard masks with the network statement. We don't have to, but we can. And again, I'm not covering wildcard masks. We've already done several labs with wildcards. We've already done several videos with wildcards, so you should know how to do wildcard masks. Again, it's just an inverse passive interface, just like before with OSPF. Passive interfaces will not send routing updates out those interfaces once they are classified as passive. One of the nice things is, how do you see the neighbors? You can do a show IP EIGRP neighbor, just like you could with OSPF. And again, it's going to show you pretty similar information. Address, interface, hold, uptime. Here we're not talking about designated routers or anything like that, so it won't pop up with that, but again, neighbor IP address, the local interfaces receiving the hellos, the seconds remaining before a declared neighbor is down. This one's going to be a countdown. We can also do show IP protocol, and that's going to give us again what routing protocol, what AS number we have, the router ID, the distance, the distance metric, if it's auto-summarized or not, and again the routing info sources. Here we have a IP route table. Again, you're going to notice the metric and total cost. We've already broken down these in both routing and switching essentials and network fundamentals, so we're not covering this in depth anymore, but I wanted to point that out again. So let's talk about the operation of EIGRP. So we talked about neighbor adjacencies, and again we talked about the different types. We talked about the hello, we talked about an update, the query, reply, and acknowledgement. So here's the process for discovering a neighbor. It will send a hello, then an update, and another hello. And then this one should take that hello and send an update. Here is the process. So router 1 will send a hello, router 2 an update, router 2 will send a hello, router 1 will send an acknowledgement of the update, and will also send an update to its hello, and router 2 will send an update. So I mean, this is based off of that, that's based off of that, and because this guy got a acknowledgement, there we go. So hello, update, acknowledgement, that hello required an update and an acknowledgement, so that's how that process works. And again, once that process has happened, they configure out the best route and converge. Composite metric is K1 times bandwidth plus K3 times delay. So what is K1, K2, K3, K4, K5? You can actually set them. Typically, K1 is bandwidth, K2 is load, K3 is delay, K4 is reliability, K5 is reliability. The K values change with the metric wait command. metric weight, TOS, and it's specific. So if we want to change the delay, just the delay, we may keep those the same. We may not set them to 0. We may set them to what they were before, and then we'll be changing that guy right there. You don't just type K3 equals, but I mean it's going to be each space is specific to a K number. So again, K1 times bandwidth plus K3 times delay. Here's an example. Bandwidth is going to be K1 times bandwidth, K2 times bandwidth divided by 256 minus the load, plus K3 times the delay, times K5 divided by reliability, plus K4. That's going to be one of the metrics that will be used. Oh, the joys of calculating metric weights. Examining the interface values. We always have done show IP, show interface brief, but we've never actually looked at the detailed output. And we're still not covering the detailed output. We're just going to go more in depth. BW, right here, bandwidth, kilobits per second. We have the delay of the interface in microseconds. Reliability, and transmit and receive. Reliability is of the interface. By default, the value is not included in the computing of the metric. But there is a reliability. Also, there's going to be a transmit and receive load. And that is, again, by default, the value is not included by that computational metric. But when you do a show interface, and you're looking at an interface now, you can specifically see more of that detail. You can set bandwidth metrics. You can look at a specific interface and change bandwidth. So most serial bandwidth is set to 1544 kilobits per second by default, but you can change the delay. So you can change the bandwidth costs, and normally the bandwidth is associated with a delay. So what are the delays? Ethernet, again, is 10 megabits per second, is a delay of 1,000. Fast Ethernet's 100 megabits per second, gig is 10, so forth and so forth and so forth. Here's where we're getting our default delays from. Again, this is 10, this is 100, this is 1,000, and there's no 10 gig here, but you get the point. So again, now that we understand the delay, let's look at how to calculate the metric again. K1 times bandwidth plus K3 times delay times 256 equals our metric. So essentially, bandwidth, delay times 256 equals our metric. So here we have our, I hate when they do this. We have our appropriate bandwidth. We have the sum of the delay divided by 10 equals that. That's how we get this giant number right here. I already gave examples of this in our Routing and Switching Essentials lecture review when we broke down this entire statement. So there's already some material out there for that. So the common thing here is, why are we doing this? Why do we care about the metric? How do we care about any of this? Big thing here is this is used for path determination. Faster the path, typically the route it's going to take. So if we understand how the metric is calculating them, then we're able to figure out the path it's going to take. That leads us into this dual concept, and this provides a loop-free path and a loop-free backup path. Provides fast convergence, minimum bandwidth usage for its bounded updates, and the decision process for all route computation is done by the dual finite state machine. There's a module in there that does just the dual calculations. It tracks all routes, including backup routes, even the routes that aren't displayed. That way, when a primary route goes down, a backup route can be brought online without much of a delay. Using EIGRP metric to select the most efficient, the loop-free path identifies the routes with the least costs to be inserted in the routing table as a primary route. Again, EIGRP maintains a list of backup routes that Dual has already determined can immediately become a fallback path. Those are just, again, the backup paths just in case. These are actually called feasible successors. So we have a primary successor. That's going to be the route it's going to take by default. We have a feasible distance, or a feasible successor, but here we're just talking about the ones that are active. We have a feasible distance. That's going to be the lowest calculated metric to reach the destination. So that's what this guy is right here. To go from source to destination, that's the metric. The lowest one is the best. Sent to that guy. We have what's called a feasible successor, and that's going to be the neighbor with the second one. We have feasible conditions, and that's when the neighbor reports the distance to a network is less than the local router's feasible distance. And then we have the reported distance. So when we're looking at that, we have other options to manipulate, like the feasible successor, feasible conditions. And as we manipulate things, our route table may recalculate a different backup or primary route and backup route. We can look at the topology table. Again, here we have our next hop, we have our feasible distance, we have our successor, we have the outbound interface. This is all the show IP EIGRP topology. Again, we have our next hop, our feasible distance, our feasible successor, and again our outbound link. Here, when we do a show IP EIGRP topology all links, feasible distance, reported distance, the successor. So you're going to notice here, this is going to be the successor. This is not a feasible successor. Here's the reported distance, and the lowest one works. So the one that's too high is not a feasible successor because the distance is too far. So again, understanding the numbers kind of do help. Alright, moving on to the convergent state, the actual mechanism that controls dual. Is it a feasible successor? And here's the flow chart you can go through. Alright, the feasible successor, again, removing destination, because when you're doing the debug EIGRP FSM, you can actually see the mechanism as dual is working. You can see it do the installing of new routes or removal of routes. You can see which ones will have feasible successors and no feasible successors. Alright, so now let's hop into our last major section, configuring EIGRP for IPv6. It was pretty dang simple for OSPF. So let's see if EIGRP is just as simple for IPv6. Here again we have two separate tables, IPv4 and IPv6, neighbor table, topology table, routing table. While they work together, they're separate tables. Comparing and contrasting, they are almost identical. Authentication is slightly different. The multicast destination addresses, again, slightly different. IPv4 versus IPv6, but pretty much everything else is the same. The IPv6, the actual sending of information is typically done using the link local address. That's going to be that FE80 address. If you want to know more about that, check out my videos on IPv6 and exchanging of information with EIGRP. Here is again our basic topology. So let's look at how we would configure it. Basically, you would be doing interface, going to that appropriate interface, setting the link local links, and at least this is again is for a link local. And then here's where we would start our EIGRP. You have to turn on IPv6 unicast routing. You have to turn on the IPv6 router EIGRP AS number, set the router ID, and turn it on. Apparently now we have to make sure we do a no shutdown command on our routing protocol so that we can actually form adjacencies with our neighbor. So how do we configure the commands so that the interfaces are working in EIGRP? Pretty much same as we did with OSPF. Underneath each of the interfaces, IPv6, EIGRP, and the appropriate AS number. We can verify with, again, a show IPv6 EIGRP neighbor. We've already gone through this with IPv4, but here's the address, the interface, the hold timer, the up timer. Here's what we would be seeing if we did a show IPv6 protocol. You could see the AS number. You can see that it's running EIGRP. You can see the metric weights, the K values, 1 through 5, the router ID, the distance and external distance, and the interfaces. Here again is a show IPv6 route. You can see the appropriate routing table. And that's it for this chapter. We talked about EIGRP being advanced distance vector. We didn't really talk about it being classless. EIGRP uses the D in the route table before the dual functionality of it. Dual, again, that's how we are measuring. Again, RTP instead of TCP. We talked about EIGRP sending partial and bounded updates, it being a composite metric using bandwidth, delay, reliability, and load. We talked about dual and how it functions. And that's the end of this chapter. If you have any questions, please let me know. Thank you.